Swayam Prabha. Digital India. Educated India.
Welcome students. In last class we discussed about the first postulate of quantum mechanics, which said that for a quantum mechanical system there exists a wave function or a state function that contains all the information about the system. However, that first postulate did not tell us how we get those information from the system. For example, if I want to know the position of that system or the momentum of the system or energy of the system or any other classical observable that I would like to know about the system, how would I do that? The first postulate simply said that there exists this state function that contains all the information that you can possibly have. We will continue our discussion further, especially to the second postulate, which gives us a recipe as to how we can get some information about the system. The second postulate says that for every classical observable, there exists an operator in quantum mechanics. So, if we want to get some idea about a system, we must ask what do we want to know about this system, and when we have answered that question, what property we want to measure for that system, then the solution to obtain that information is to bring that operator which is provided by quantum mechanics. In today's lecture, we will discuss we will try to get some more ideas about what this operator is and how we can use to get information about the quantum mechanical system. In quantum mechanics, as the second postulate said, that we have an operator for every classical observable. Now, in classical mechanics, we would, or when we have prepared a system, we would perhaps want to know a few dynamic observable about that system. For example, one common thing that we are always interested to know is that what is the position of the particle. So, position is given by an operator x. Any operator in quantum mechanics is denoted by a hat on top. So, x is the position operator. What is its function? An operator is essentially a rule or a command that gets carried out. So, this operator x is simply the action of it is multiplication by x, which is the variable along that dimension. So, as if I have defined my position as in the x coordinate as x cap or the operator x, similarly I can do that y cap would be the operator to get the position along y axis, whose action is simply multiply by y, or z cap is the operator that gives me idea about the position along z axis. The other quantity that we would like to know is that what is momentum. So, the classical observable momentum corresponds to a quantum mechanical operator, and this quantum mechanical operator along x axis is given as minus I h bar. I is the imaginary root, h bar is the Planck's constant, h divided by 2 pi, and I am using a partial derivative notation which says that d by dx. So, this operator means the momentum operator, I give it as p x momentum operator with a hat, and its action is that you multiply it with minus I h bar and differentiate with respect to x. Similarly, if I define my p y, which is minus I h bar, the partial derivative with respect to y, and p z minus I h bar d by dz. The partial derivative, the reason why I am using partial derivative is that p y differentiates the function only along y direction, but the function may have dependence on x and z, but this corresponds only to the partial derivative. But if your function has only one dimension, either x or y or z, so then this partial derivative becomes normal derivative. If I know the momentum, then I can get the kinetic energy, which is given by T, or even sometimes you would see K cap. So, that the hat represents that I am talking about an operator. So, this operator, we know the kinetic energy is simply p square divided by 2 m, that momentum square divided by twice the mass. So, I can use the same relation here. So, I can see the momentum would be p x square divided by 2 m. So, how would I get that? I would get this by p x square by 2 m plus p y square. So, this is which is essentially, if you solve it, you would get so this is the expression for the kinetic energy operator. The potential energy operator V, this is potential energy, is often multiplication, the action of this potential energy operator is often multiplication by V, which is often depends on the coordinates x, y, z. So, the action of potential energy operator is simply multiply the potential energy with the function that is coming. So, now we have discussed about the position operator, the momentum operator, the kinetic energy operator, the potential energy operator. So, the total energy operator, if we want to obtain the total energy E, if the observable is total energy E, the quantum mechanical operator corresponding to this energy is called as Hamiltonian, which is given as H hat. The Hamiltonian can have kinetic energy term plus potential energy term. So, for what we are discussing is that if I want to determine the position, I have the wave function which contains all the information, but if I want to measure the, if I want to ask the system what is the position of my particle, then I must bring the position operator, which is x, y or z. If I want to determine the momentum, then I must use my momentum operator. If I want to use the kinetic energy, I must bring my kinetic energy operator, and if I want to measure the total energy, then I should bring the Hamiltonian, which is actually the energy operator. The other quantity that we would actually come across in the course of our discussion would be the angular momentum. We know we define angular momentum L as r cross p, it is a vector product between r and p. So, since we know r which has x, y, z dependence, I know p which has p x, p y, z. So, therefore, the quantum mechanical operator corresponding to L x I can write as y p z minus z p y. These are all operators. And what is the action of y operator? The action of y operator is simply y, and what is p z? This is minus I h bar d by d z. I see p z is here, and what is the action of z operator? Simply multiplication by z, and what is p y? That is minus I h bar d by d y. If I solve this, I would have minus I h bar y d by d z minus z by d y. Now, this is the quantum mechanical operator corresponding to L x. Similarly, I can define the operator L y, the operator L z, and so on and so forth. So, what we learnt is that for every classical observable that I wish to know about my quantum mechanical system, quantum mechanics offers me an operator. So, to gain some insight about the system, which all the information are there in the wave function, but to get any particular any idea about any particular observable, I must bring that quantum mechanical operator which corresponds to that classical observable. Okay. Next we would discuss some properties of operator. Suppose I have an operator A and I have got another operator B, and I am applying this operator A and B together on a function f. When an operator acts on a function, it transforms the function to either itself or another function. The operator is simply, as I said, the operator is simply a command that gets executed on a function. So, operator A plus B is when they together act on a function f, we can also evaluate this as individually A acting on f plus individually B acting on f. So, this is the sum rule that the operators follow. Similarly, there is a product rule. So, if I have operator A multiplied by operator B and they act on a function f, then I can do this as I first keep operator A and first apply operator B on operator f, and then this would be when operator B acts on an function f, then I may get a function, I am calling it g, and now this function which is coming because of the action of operator B on function f will be acted upon by operator A, and then again it may give me another function h I can write. So, this is where this is the product rule, this is the sum rule. We would now use we would apply these two rules by taking two operators and an example function. So, in our example we will take, let us say A, operator A is our position operator and operator B is our momentum operator, and I am using only x along x direction. So, and let us define our function f, which is simply a sin x function. So, what would be the action of A plus B? That should be x minus I h bar d by dx and the function sin x. So, I see that first I can apply the operator x on this function. I know the action of operator x is simply multiplication, multiply it by x. So, x sin x minus, now I am applying the second operator minus I h bar d by dx on sin x. So, I see minus I h bar comes out, and then I have to differentiate this function. So, what do I get? So, I have x sin x minus I h bar cosine x. When I differentiate sin x, I would have cos x. So, now the action of operator A plus B on a function f is given here. Now, we will do the same, but now we will use the same operators A B, but we would apply the product rule. So, now what do I have? X operator so, we know that if there are two operators A B apply which are multiplied and they are being acted on a function sin x. So, I can apply the second function first onto the wave function. So, I have x, I keep it outside, and then first I see what this does. So, I am applying the second function second operator b onto the wave function the function sin x. So, I see the result of that is a cosine function, and now this function is being acted upon by the operator a here. So, I know action of operator x is simply multiplication. So, therefore, my result is minus I h bar x cos x. this is what this is how I evaluate the product rule. I will continue this discussion. Instead of doing this product as A B, can I, if I do B A product and apply it on a function f, what would I get? So, B is my momentum operator, A is my position operator. When I do that, I first write down I minus I h bar d by dx. This is the second operator, they act on the wave function sin x. Now, when I have these two operators, first I apply this operator over here. So, I am writing down the first operator as it is. The action of x is simple, x sin x. So, now this is a new function which is obtained after application of the operator x onto the function, and this new function will be acted on by this operator, the momentum operator. When I see here, I see that I have to differentiate d by dx, but a function which is product of two functions x sin x, and I will have to be careful here because I will use the product rule. So, I first take out x and differentiate sin x, or take out sin x and differentiate x. So, then when I apply B A on function f and I apply A B on function x function f, I see the results are different. So, therefore, the operator algebra is not necessarily always commutative. So, what I see is that A B f is not equal to B A f. So, this means, in other words, I say operator A and operator B, they do not commute. If A B action of operator A B on f would have been equal to the action of operator B A on f, then I would have said that the operators A and B commute. However, in the example that I showed here, the operators do not commute. We will come back to this commutation relation between operators in our future classes, but we will continue our discussion on further some properties of the operators. Another important properties of another important set of operators are known as linear operators. I define an operator A and I would call it a linear operator if it satisfies two conditions. Condition number 1 is that if I apply my operator A on two function f of x, g of x, if it is equivalent to applying the same operator individually to applying the same operator to these functions individually. This is first condition, and the second condition is that where C is a real constant. So, if I multiply my function f of x with a real constant C and the operator A applies on it, if it allows my C to come out of the action of operator A, and if the left hand side and the right hand side are equal, then the operator can be a linear operator. So, these are the two essential conditions before I can declare that my operator is a linear operator. So, let us take an example. Let us say my operator is a square root operator. What does a square root operator do? A square root operator, when it acts on a function, it simply gives you the square root of that function. So, suppose, so do you think this would be a linear operator? let us find out. Suppose if I have f and g as a two function and I am taking the square root of them, the left hand side would be the right hand side will be square root of f plus square root of g. This is not correct. So, therefore, I provide this inequality and therefore, the square root operator is not a linear operator. Even in fact, it also does not satisfy the second criteria, that if I take a constant c, real constant c and multiply with the function f and take a square root, this is not equal to this. So, therefore, the square root operator is not a linear operator. Similarly, you can show if the operator A is a square operator instead of a square root operator, square operator would simply square the function, that also would not be a linear operator. Now, we will take an example as d by dx. Is this a linear operator? Let us find out. Suppose we check the first condition, d by dx acts on f of x plus g of x. We know from our knowledge in calculus that we can write so the first condition is first criteria is met, first criterion is met, this equality holds good. So, let us look at what happens to the second one. So, if I multiply this, then I know if the c is real and c is also a constant. So, it is independent of x. So, therefore, I can bring c out of the differentiation. So, therefore, the operator d by dx is actually a linear operator. Linear operators play a very important role in quantum mechanics. In fact, all the quantum mechanical operators that correspond to a classical observable are linear. So, the operators that we discussed for example, the position operator, the momentum operator, the kinetic energy operator and so on and so forth, they all are linear operators. So, in this course most of the operators that we will discuss would be linear operators, and when we say linear operators we have these two essential conditions in our mind. So, just to summarize the state where we are, the first postulate suggested that there exists this wave function which contains all the information, and the second postulate told us how to get some information. The second postulate's recipe to get some information is that if you want to obtain some idea about a particular classical observable, then you go and find out what quantum mechanical operator does this classical observable represent, because quantum mechanics guarantees us that for every classical observable there exists a quantum mechanical operator. So, we looked at some properties of the operators, and now we would continue our discussion and take forward to see how operators and functions have a relation with each other. So, let us explain this in terms of some examples. For example, if I take an operator d by dx and act this operator on a function sin x, I know that I would get cosine x. So, what this operator did to this function is that it changed the function from sine function to a cosine function. If I use the same operator, but apply it on a different function, for example, I apply it on x square, then I get 2x. Again, the operator changed the form of the function from x square to 2x. I will take a third example. The third example is that when I differentiate a function which is e to the power a x, the differentiation of this function would give me a multiplied by e to the power a x. In the first two cases, the operator acted on a function and gave a new function. In the third example, the operator, the same operator d by dx, the same differential operator, when it acts on a different function, in this case an exponential function e to the power x, it actually gives back the function itself. It does not give a new function, rather it gives back the function itself. Let us look at yet another example. The second example is second derivative d square by dx square. if I apply this function on sin x, so this essentially means that I have to differentiate sin x twice. So, first time when I differentiate I will get cosine x, and then I will have to differentiate cosine x again, which will give me minus sin x. So, therefore, that would give me minus sin x. And here you see that the function I started with sin x, and after the operation of this operator d square by dx square I get minus sin x. The function actually comes back with a minus sign. So, let us look at the action of d square by dx square on x square. So, the action of this the first derivative gives me 2x, and when I differentiate it again I would get 2. So, what I see is that this function x square upon when I act this function when I act d square by dx square on this function, then I am getting another function which is 2 now. So, I would do the same for the third function. What I get is that when I d square by dx square acts on this e to the power a x function, I get back the function multiplied by a square. So, we see that there are two different types of functions. In the first set of examples, sin x and x square got transformed to different function, whereas e to the power a x got back the same function. We got back the same function after acting the operator d by dx. So, in this case, when the action of operator reproduces the same function multiplied by some constant, then this function is not merely an ordinary function, rather it is a characteristic function of this operator, and this goes by the name Eigen Function. Eigen word is a German word which means characteristic, and this e to the power a x is an eigen function of operator d by dx. However, sin x and x square are not eigen functions of operator d by dx. On the other hand, when I look at d square by dx square, sin x is indeed an eigen function of the operator d square by dx square, because it gives me back the function itself multiplied by a constant minus 1. What about x square? X square is not an eigen function of d square by dx square, because it does not give back the function itself. On the other hand, again e to the power a x is again an eigen function of d square by dx square. So, here what we see is that sin x is not an eigen function of d by dx, but is an eigen function of d square by dx square. X square is neither an eigen function of d by dx nor an eigen function of d square by dx square. E to the power a x on the other hand is eigen function of both d by dx as well as d square by dx square. So, we see that there are some functions which are eigen function of some operator. So, eigen function, when we define eigen function, we always have an operator in our mind. The eigen functions cannot exist in vacuum. Eigen functions, when we define an eigen functions, they must be an eigen function of a particular operator, and the constant that we obtain out of this action of an eigen function is called the eigenvalue. For example, when we acted sin x by d square by dx square, we got minus sin x. So, minus 1 is the eigenvalue, or when we acted e to the power a x on d square by dx square, then we got a square as the eigenvalue. So, today we discussed about the eigen functions and eigenvalues, and we will continue our discussion in the next class. Thank you very much.